Hello and welcome to Physics with Amol sir. So this video is for class 12 and we will continue with moving charges and magnetism. So previously we saw the Ampere's circuital law. Okay, now that law will help us to find out the magnetic field at any point. Today we are going to talk about the force that will act between two parallel current carrying conductors. Okay, so let's begin. Okay, so here we have two conductors. Let us call them conductor A and conductor B. They are infinitely long, okay, and they are placed parallel to each other. There is some distance between these two conductors. Let us say that distance is equal to small d. Okay, then there is current flowing through these conductors. From conductor A, the current flowing is IA. In conductor B, the current flowing is IB. In the beginning, let us imagine both the currents are parallel to each other. That is, they are moving in the same direction. Okay. So now, what is going to happen? Because of current that is going in this conductor, this will create a magnetic field around this conductor. Okay. Similarly, because of the current going in B, there will be magnetic field around B. This will result in a force being exerted by these two conductors on each other. Correct? Because there is going to be a magnetic field around B and magnetic field around A, which will interact with each other and a force will be exerted. So the task for now is to find out how much force will be exerted between these two conductors. Now, let us say because of this conductor A, that is current going in A, there is a magnetic field at B, okay, and that magnetic field, let us call that as capital B A. Okay, we are giving it a subscript of A to show that this field BA has been created by the conductor A. Right. So because the current is going like this, okay, by the right hand rule I can find out the magnetic field on this side is going to be in this manner. Correct? So the direction with the sketch pen I can show at this point the magnetic field will be outwards like this. Getting the idea? Okay, so to show that we can draw a dot for this. So there will be magnetic field around the entire conductor B because of A. So BA is a magnetic field on the conductor B and it is pointing outwards because that is given to us by the right hand thumb rule. Okay. Now because of this magnetic field and the current that is going here, there is going to be a force. I am sure you remember that equation. F whenever there is a current flowing in a conductor, force is given by IL cross B. Okay. So let us imagine this particular length. The length is equal to capital L. Correct? So on this length there is going to be a force. So we have current that is going upwards. We have magnetic field that is pointing outwards. So again, using the right hand we can have I is the direction that is current is going upwards. So IL cross B because B is pointed outwards. So again you will see IL cross B. My thumb is pointing from left to right. So this will be the direction of the force. Let us call that force as FBA. By BA, it is the force that is going from B to A. Okay. So, or we can say that is a force on B due to A. So this force that is on B due to A will be in this direction. Okay. Now let us find the magnitude of this force. So I will write it as FBA equal to, already direction is known. So here I will mention only the magnitudes. So FBA will be IL cross B. How much is the current? Current is IB. Okay, IB. Then how much is the length? It is equal to capital L. And how much is the magnetic field? BA. Okay. So FBA will be equal to IB into capital L into BA. So let us call this equation number 1. Now we can find out this magnetic field that is BA by using the Ampere's circuital law. Right. So using Ampere's circuital law we will get BA into L will be equal to mu naught into IA. Correct? So that is magnetic field BA multiplied by the total length. Okay, that could be the length of this Ampere loop over here. So BA into L will be equal to mu naught into A. Mu naught into IA. So therefore BA will be equal to mu naught IA upon the total length. And that Ampere loop, the total length will be equal to, as it is a circle, we can write it as 2 pi into d. So 2 pi d. So BA is equal to mu naught IA upon 2 pi d. Let us call this equation number 2. Then using equation 2 in equation number 1, we will get FBA equal to IB into L. BA, that will write as mu naught into Ia upon 2 pi d. So we can rearrange this properly and we can write this as mu naught Ia Ib into L upon 2 pi d. So that is the magnetic, this is the force that is exerted on B due to A. Now if you do the same kind of treatment for this conductor, that is A, you will find that the force that is exerted on A, that is FAB. Okay, you will get that FAB will have the same magnitude, that is mu naught Ia Ib L upon 2 pi d. You can actually try to do that, but the direction will be opposite. That is, this FAB will be in this direction, that is like this. Correct. So that is the force that is exerted on two parallel current carrying conductors. Now if both the currents are in the same direction, you will see that there will be an attractive force. The conductors will move towards each other. But if let us say the currents are anti-parallel, correct? Suppose here the current is going upwards, in B it is going downwards. In that case, it will be the forces will be in the opposite direction. So that we will get a repulsive force. Okay, remember. So if the currents are in the parallel direction, they will attract, and if they are in anti-parallel direction, they will repel each other. Okay, so this is the derivation for force on parallel current carrying conductors. Okay, now the next derivation is to find out the torque acting on a current loop. So we are going to imagine a rectangular current loop. So this is our current loop A, B, C, D. Now I hope you remember this kind of diagram. In 10th standard, when we had studied about electric motors, okay, that time I'm sure you remember same diagram we had seen. So this is nothing but an electric motor, the setup for a motor. So we have the armature ABCD that is connected to the slip rings, which is connected to the power supply, and this is placed in a strong magnetic field which is going from north to south. Okay, here what you need to remember, we have a magnetic field that is going from here, that is left to right. ABCD, that is our current carrying loop. Okay, so we can have either a single wire or we can have multiple number of loops. We have connected in such a manner that current is flowing from A to D right now. Okay, and we are imagining a rectangular loop so that it is easy for us to derive the formula. Okay, so now what will happen is, one thing that we have to write first, this length BC and AD, let that be equal to small a, and this length AB and CD, that will be equal to small b. Okay, so we are following the same nomenclature as in the textbook. So anyways, so in the initial stage, we are going to imagine the plane of this loop is completely parallel to the magnetic field. Okay, so if this is our loop ABCD, it is completely parallel to the magnetic field. Fine. So magnetic field is equal to capital B. Okay, and the current that is flowing through the loop is equal to capital I. That much is, I am sure, clear. Now what will happen? There will be a force acting on this current loop because of the magnetic field, and that force will be given to us by IL cross B. Okay, remember this equation. So now let us see the loop, the part AB first. On AB there will be force IL cross B. Now this is the direction of IL, okay, upwards. Whereas B, it is going from left to right. So IL cross B. My thumb is pointing inside. Okay. So the force that is on AB will be going inside. That is perpendicular to this board, but in the downward direction. Correct. Then on BC, IL cross B. This is the direction of IL in this direction, and that is the same direction as magnetic field. So the theta is going to be 0, and sine of 0 will be 0. Therefore, no force on BC according to this formula. For arm CD, there will be a force given by IL cross B, but now theta will be 90. So therefore, we will get force given by ILB. Correct. And direction will be outwards. Why outwards? Current is going downwards. Magnetic field is from left to right. Okay, so we curl our fingers like this. The force will be outwards. Again on arm ED, the same case as on BC. IL cross B will give 0. So there will be force acting on AB in the downward direction and CD in the upward direction. This force on AB, let us call that as F1. F1 will be IL cross B. As I told you, sin theta will be 1, so we will only get ILB. How much is the current? I. How much is this length? This length we have already determined as small b, and magnetic field is capital B. So this is F1. On CD, the force, let us call it F2. F2 will be equal to, again, I will be, so which will be the same, I into small b into capital E. What is different between these two forces? F1 is pointed inwards, Fb is pointed outwards. So net force acting on our current loop is going to be 0. Okay, why 0? We are getting two forces of same magnitude but opposite directions. So net force is 0. But as you would have definitely noticed, the net force is 0 but torque is not 0. There will be a torque that is going to act on this this rectangular loop. Okay, because of this torque, this particular loop is going to start moving. Okay, how it will move? If you are looking from the top, it will move in this direction. Okay, that is in the clockwise direction. It is going to start moving. So now let us find the torque that is going to act on the loop. Okay, torque will be given by the magnitude of force multiplied by the distance. Okay, so force we have determined as F. So either F1 or F2, it will be I small b into capital B multiplied by the distance. How much is the distance? It is equal to A. So I can write torque is equal to force. I can write by any of these, I into small b into capital B multiplied by A. Or if I rearrange this and write, I will write this as I into AB multiplied by capital B. Now A into B, that is length into breadth, that will be nothing but the area of our loop. So this I can write as capital A, and so I will get torque is equal to I capital A capital B. This expression will give us the torque acting on our loop. Okay, so what we saw, the torque that will act on our loop, that will be given by I A into B. But what was the condition we imagined? That the loop was exactly parallel to the magnetic field. If that loop is not exactly parallel and makes some angle, okay, let us say it is making some angle theta with regards to the magnetic field. In that case, the torque we will get is given by I AB sine theta. Okay, so that will be magnitude of the torque. Here this theta will signify angle between the magnetic field and the area vector. Okay, now I hope you remember we had discussed this topic, that there are some scalars which are actually represented as vectors. So area is a scalar quantity, but here we will represent it as a vector quantity. Okay, and how do we give a direction to that vector quantity? Again, we use the right hand thumb rule. Okay, so we will use the direction of the current. Okay, and the thumb will give the direction of the area vector. Okay, so you can write the formula for torque in terms of in the vector form like this. So the vector torque will be written as I into area vector cross B. Okay, and this term I into area vector, this is actually called as the magnetic moment. So we will get torque equal to magnetic moment M cross B. Okay, so this is torque acting on a rectangular current loop. Okay, so from this we see the definition of magnetic moment. So magnetic moment vector is defined as the product of current and area vector. Okay, so this is the definition of magnetic moment. Now magnetic moment, this is a very important concept. Basically to find out magnetism, that is the concept of magnetism will be understood by the moment vector. Okay, so it is very important to understand. So M is equal to IA. Of course, the direction of magnetic moment will be the direction of area vector, okay, which will be given to us by the right hand thumb rule. And the SI unit of magnetic moment will be Ampere meter square. Okay, so understand, make sure that you note down this concept. So just like in electric fields, we had the electric dipoles, correct? Similarly, in magnetic field, we'll have the magnetic dipole. Okay, so that is why dipole moment. So that is why this concept is important. These two are analogous concepts. So similar to the electric dipole, we have the magnetic dipole moment. Okay, so I hope all these concepts were understood. Make sure that you go through the solved examples in the textbook and all the examples that I have given in the notebook. Okay, in the exam we could have questions, that is the derivation based questions as well as numericals on these topics. Okay, so that's all for today. If you are having any doubts, make sure you are asking me, right? And make sure that you complete the notes till this topic. whatever derivation we saw today, I have given given all these questions in the notebook, and all the steps are already mentioned over there, and along with the solved examples. So make sure that you go through them. If there are any doubts, make sure you are asking. Thank you.